Welcome to EDU World Space.
Okay, in this problem, we have a convex lens with a radius curvature of 18 centimeters, and we have an object that's 3 millimeters tall and 18 centimeters away from the lens. We're first asked to show that this image, the resulting image, is virtual, and we're asked to find its distance and height of the image. So the only two equations we'll need for this is the ideal lens equation, 1 over the object distance plus 1 over the image distance equals 1 over the focal length of the lens. We also are going to use the fact that the ratio of heights, which we call m, is equal to the negative ratio of distances for the image and the object. So we're going to do a bit of ray tracing. It's going to be not as nice as it could be with these non-straight lines, but I'll show you the idea. So here's our lens, and here are the 3 principal rays going through the lens. Notice they all deflect off the lens, the main rays, but virtually an image is formed behind the lens, which has a certain height, and you can determine its height by looking at the intersection of these 3 principal rays. So the image has to be virtual. It's going to be behind the lens. That's always the case. If we assume a focal length of negative 9 centimeters, as it asks in the part B, we can use the ideal lens equation, recast it in this form using just a bit of algebra to find di. When we plug our numbers in, we end up with negative 6 centimeters. To find m, to ultimately find the image height, we use the definition of m, that the ratio of heights is equal to the negative ratio of distances. And then we've recast this using a bit of algebra to get the image height, where we know the object height and we know the image distance and object distance. We have everything we need. We can find the height to be 1 millimeter. And that's it, just using the lens equation and the definition of m and a bit of ray tracing. And that's it.